Hello, right, here's another couple of circuit components that I'm going to describe in a little bit more detail. So ammeters and voltmeters, we're using these all the time, whether it's in the lab or in our questions where we're drawing out circuit diagrams and such like. So going to unpick a little bit of what's going on inside these things. They're very similar, that's why I'm putting them in the same video. So let's start with ammeters. So ammeter, short for ampere meter. As we know, that's measuring electrical current. We know that it has to have low resistance, and we know that it's put in series in a circuit. And it has to have low resistance because, of course, the more resistance you've got, it affects the current. And if we're measuring the current and introducing resistance, then we're actually changing the thing that we want to measure, which isn't what we want. They have an obvious historical origin. So if we go back to the time of Hans Christian Ørsted, this is the guy who observed the deflection of a magnetic needle by a current carrying wire. This is something you've probably done in the lab at some point. You've got a wire, you've got current flowing along it. We know that we've got these sort of circular magnetic fields that are then set up around the wires in the circuit. So if you put a magnetic needle near to, or a compass, something like that, near to the current carrying wire, the needle will deflect. So this is the basis, really. This is the foundation of how an ammeter is going to work. Just need to calibrate this deflection and engineer things a little bit better, because there's a number of things that we want to do engineering this. I mean, we need to have something that's going to move the needle back again once the current is turned off, because it's one thing to deflect something to a new position, but you need something to move it back. So you can do that using maybe gravity, or as they mainly did in the very first ammeters, is they aligned the instrument to the Earth's magnetic field in a particular way. So it would then just move back. So if you've got a compass, you deflect the compass, you see it then moves back again once you turn off the current. So there is, an obvious way of moving the needle back to the zero position. We know for if we've got AC, if we've got our alternating current, the needle is going to deflect in both directions because the direction of magnetic field is going to change. It's going to alternate with the alternating current. So, you're going to want to have a needle in the middle and then deflecting in both directions. The first ones that were really engineered, they were called galvanometers. Galvanometers are more or less the same as ammeters. The early ones, these were measuring direct current. We've got this same stem here that we've seen on in a lot of the videos that I've done recently. So this is going back to Luigi Galvani, the guy with the frog's legs, who he stuck a couple of different electrodes of different metals into the frog legs, which more or less created a mini battery, and they started twitching. So you get a lot of things named after him. So galvanometer, a meter for measuring the effect that he discovered, as in meter for measuring electric current. We see people talking about galvanomic circuits and such like, which we just call electric circuits nowadays. So if we're going to engineer this a bit differently, you want to have more control, maybe more sensitivity in the needle. So you tend to get a magnet with a coil inside. So the circuit is then running through this coil. This is attached to the needle, and you just get a more controlled and better deflection on the needle. The trouble with this is they were only really working for DC, so they had to have new ways of engineering things in order to cope for alternating current. So they started using things like electromagnets, or what's called moving iron ammeters, because you can't just have the needle flicking around. The frequency of alternating current is these are pretty high frequency oscillations, and you're just going to get this sort of blur of needle movement on all of this. So it helps if you can get an easier to read movement. And the idea with these moving iron ammeters is that you'll be taking advantage of electromagnetic induction, inducing magnetic fields in two different bits of iron. So whether we've got AC or DC, whatever happens, those magnetic fields are going to repel each other. So we're getting the same direction of needle movement then, which means you're going to get, whether you've got AC or DC, it's going to flick round and it's going to, okay, that's what our current is, rather than having this continual flying around of the needle. It's notable with the moving iron ammeters, because there's still some of them you come across every now and again on old equipment and such like. They're notable for having non-linear scales. So if you see the dial on there and it's going from, you know, whatever to whatever, you'll get a sort of near linear bit on the scale. So I don't know, it might be going from 4 to 10 or whatever, I don't know, on amps. And then, but you'll find that 2 might be there or something, and then you'll have 3 here or something. You get some really weird non-linear bits on the scale, and then you get a nearly linear bit for the current that you're most likely to be measuring. So these are just engineered to the particular current range that you're probably going to be interested in. Of course, there is the question with alternating current is, what are you actually measuring on this? Because we know with alternating current, with the way that it's working, it's going from positive to negative. Okay, that line's axis is going to be going through the middle. The average current is going to be equal to 0. So what is it that we actually want to measure on the ammeter? Do we want to measure the peak? Is that what we're after? Are we looking for some kind of RMS, a root mean square current? This is coming back to the sort of issues that we had when we were looking in thermodynamics with ideal gases. What are we talking about with the velocity? Are we talking about some kind of peak, some kind of average, some kind of RMS? It's, you just need to know what it is you're actually measuring when it comes to alternating current. Right, so moving on to voltmeters then. So with voltmeters, analog voltmeters, and I'll get onto the digital ones and also the digital ammeters in a bit, but the analog voltmeters, where we've just got the needle, they're essentially high sensitivity ammeters in series with a resistor. So we take this setup that we've got with the ammeter, we then put a big resistor in the way, and then rather than putting it in series, so if this is our magnet with our coil and all the rest of it, we then put it in parallel. Now we want this to be high sensitivity because this resistor is going to be high resistance. It's going to have very small current going through the coil now. So we want to have a high sensitivity deflection here. We want to be able to measure very small currents essentially, and then you just recalibrate the movement of the needle according to potential difference rather than the current. So you're just changing the scale really on the readout, but it's the same principle. We got the same thing going on there. We've just stuck a big fat resistor in next to the movement of the coil. Now, digital voltmeters, again, very similar to digital ammeters, and I think whereas analog voltmeters were born out of analog ammeters, the digital ammeters were born out of digital voltmeters. So it's difficult to get into the details of these because we start getting into some complicated electronics. But it was in the 1950s that people started inventing and building these digital voltmeters. And you've got, in terms of the amount of resistance, this resistor that we're sticking here, you might be looking at, we're looking at, so I don't know, 10 mega ohms up to maybe a giga ohm or something like that, depending on how expensive the voltmeter is. The higher the resistance, normally the more expensive the voltmeter, because you need a better ammeter, in inverted commas, attached to it. It's got to be more sensitive. The more we increase the resistance, the more sensitive the equipment has got to be, which adds to the cost to some degree. So we're still using this same basic principle, and you've still got an analog component inside the digital voltmeter, and then you need what's known as an ADC, an analog to digital converter. So this is some complex electronics. but we've seen at least sort of some basics of what's going on when we were talking about transistors and switching and storage and things like that. So you can get some idea, I suppose, of what's happening. If you've got your small current that's passing through this voltmeter, we can then store information about that current in transistors, capacitors, and such like. And then if you've got a particular sample rate, then you can read out, you're more or less downloading this stored capacity that you've been saving in the electronics inside the silicon chip inside your electronics. You're sort of saving stuff in these components, and then you're reading it out every so often based on a particular sample rate. So although the electronics are very complicated, I mean, they're beyond not only this video but also my understanding of electronics, at least we can get some idea. We can imagine what is happening to some extent based on our primitive understanding of storage in transistors, capacitors, and things like that. And again, the ammeter and the voltmeter from the digital side work in a very similar way. But all of it is underpinned by this foundational idea of the deflection of a needle based on that magnetic field, which is formed around a current carrying wire. And then it's just left to the engineers. I say just left to the engineers. It's left to the genius of the engineers then come up with ways of exploiting this physics of the universe and then turning it into something that's really useful. So there you go, another couple of common circuit components.